This lesson is on the square root function. What are squares and what are their roots? Let's take the first few numbers here and square them. What do you get? You get the perfect squares. Perfect square numbers are numbers that take an integer squared and it makes the perfect square. So 3 squared is 9. 9 is a perfect square. Perfect squares also have nice roots because if you take the square root of 9, you get 3. Basically, you're saying what times what gives us 9? Well, we know 3 times 3 gives us 9. So since 3 squared is equal to 9, then we know that the square root of 9 is 3 because the square root, a root, asks us where is it coming from and therefore is asking us what squared gives us that number. You'll notice that for 9, you could have also had -3 squared equals 9, but we're not going to consider those. We're only going to consider the principal root. And the principal root is the positive version. So here are the perfect squares mapped out on a numbered line, and we're going to use that to our advantage to be able to estimate other roots that are non-perfect squares. First, let's define a square root. A square root is defined to be the reverse of a squaring operation. The mathematical definition is if we take the square root of a and that equals b, then that is only the case only if b squared is also equal to a, and these statements are equivalent to each other. So let's use that to find the following roots. When we take the square root of 16, we're asking ourselves, what squared gives us 16? Well, 16 should be recognized as one of the perfect squares. You should become familiar with these numbers because they're going to be helpful in your understanding of where the numbers are being placed. So square root of 16 should be 4 because 4 squared is 16. Similarly, root 64 would be 8 because 8 squared is 64. In the same manner, 81 is 9 squared, therefore root of 81, the square root of 81, is 9. Notice that the square root doesn't have a little 2 here to indicate that we're looking at squares, but it could. So in the future you'll see cubes and to the 4 and other numbers here which indicate the exponent that they are considering. For now we're looking at square roots. So square root of 20. Now 20 is not a perfect square, but 20 lies pretty much in the middle of 16 and 25. So that should be giving us an estimate of between 4 and 5. So let's estimate 4.5 and let's check on our calculator. The calculator has a method for approximating roots. Square root of 20 is actually, 4.472, which is rounded to 4.5. So knowing your perfect squares gives you an intuition for what your square root should be if it's a non-perfect square. And the square root of 50, let's see where that is. Well, that should be right by 49, which is right a little bit bigger than 7. So I'm going to guess 7.1. Take the square root of 50 on your calculator and you get 7.07, which is rounded to 7.1. If they don't ask how many places to round to, then you can choose. However, quite often it's to 3 decimal places. Let's continue on. Here's some terminology on the names of things in a square root. So the root symbol, the square root symbol, is also called a radical sign. Underneath it is the radicand, the item being rooted, and the radical is the entire expression of the square root. Let's take a look at evaluating the following roots. Some of these, if we know our perfect squares, we can complete without the use of a calculator. However, some of them we may need to use a calculator. This one here is derived from the perfect square 64. 64 was 8 squared, but it has a decimal. So that would mean that we'd have 0.8 squared. Let's check. Is 0.8 times 0.8 equal to 0.64? Yes, it is. Therefore, that is its root. Root of 1/25th. Well, what times what gives us 1/25th? That would be 1/5 times 1/5 gives us 1/25th. Therefore, the root of 1/25th is 1/5. Now, what times what gives us -4? Whoa, hold up. What times what is -4? Well, how do we get a negative from the same symbol multiplied by itself? These numbers have to be the same. So if we had a plus or minus and minus, there's no possible way for us to get a negative. So this actually is non-existent. There's no possible way of attaining a negative and a root, because there's no possible way to square a number and get a negative. So we would just write DNE, which stands for does not exist. Next question, we've got a negative, but it's on the outside. So we just let it hang. Let it hang out outside, no problems there. We're now looking at what's the square root of 0.25. We know that 0.5 times 0.5 gives us 0.25, so it would be 0.5. Square root of 2, what times what is 2? I can't think of anything, can you? 2 is actually a prime number. You'll notice eventually that if you take the square root of a prime number, it's usually going to be an irrational number. It's not going to give you a nice number. So we're going to need to use a calculator to approximate this root if it's asking us to evaluate. Eventually, these can be left just like this. If they can't be broken down, they'll be left alone. But since they say evaluate it, they want us to actually calculate an approximation to it, and the calculator tells us that the square root of 2 is approximately 1.414. If you squared that, you get approximately 2. This is approximation, it's not an exact value. So later on, when we're looking at exact values, we'll want to be leaving certain roots alone, but you'll see that in a little bit. So 3 root 5, what operation is right in the middle there? Well, it's actually a times. So we're going 3 times the square root of 5, and to approximate the square root of 5, we can use our calculator. 2.236, and that's approximated, rounded to 3 decimal places, and multiplied by 3 gives us 6.708, another approximation. Try approximating the following. We've already calculated root 5, so 2.236 plus 1 and divided by 2 should give us approximately 1.618. Now, here's the formal definition of what I was indicating earlier about higher powers. If you have a little number here that's not a 2, in which case the 2 is usually not written. But if you have a different number here, it indicates that you'd have to take it to that power to get there. So in this case, cube root of 64 means what cubed gives us 64. That's what it's asking us. So what times itself 3 times gives us 64. Now, what do you think that is? You could break down 64 and you'd notice that 64 is made up of 4 times 4 times 4. You could actually prime factorize if you would like to have a nice exact value. You could also use your calculator, and when you type it in, you'll also see that the cube root of 64 is 4. Now, next up, we have a cube root of a negative. Can that happen? Can we take a cube root of a negative? We couldn't take a square root of a negative. A cube root of a negative implies that something times itself 3 times will give us a negative. Is that a possibility? Well, if all of them were negatives, then it would result in a negative. So it is a possibility. Notice that if you have an odd number on your root with a negative, that's fine. You'll still get a negative. But if you have an even number with a negative, that's not possible. Does not exist. Okay, so what times what times what? It's the same number 3 times, gives us 125. Let's try 5. 5 times 5 times 5 gives us 125. So, therefore, negative 5 cubed gives us negative 125. So the cube root of negative 125 is negative 5. Next up, we've got the cube root of 1 over 125. You'll notice I did change this because I wanted it to be a nice exact number. So 125, the cube root of 125 is 5, so then that would imply 1/5 cubed would be 1 over 125. Next, a negative on the outside of a 4th root, so that's fine if it's on the outside of an even root. 4th root of 81. 81 is 9 times 9, which is 3 times 3 times 3 times 3. Therefore, negative hangs out. 3 to the 4 is 81, so 4th root of 81 is 3. Let's take a look at how to graph a square root function. So, let's just begin by plotting some points. Quite often we start with 0, so let's start with 0. That means that y should be the root of 0. The root of 0 is 0, so 0, 0 is a point. Let's continue. Often we choose 1. That would mean that y would be the root of 1, which is 1. So you have 1, 1 as another point. If you stopped there, you might think it's just a straight line between those 2 points. However, it's a square root function, so it should make you think that it's not going to look like a line. It's got something funny on the x, like this root symbol. So, in particular, with things that are not lines, we want to plot as many possible points as possible because the shape might be different than a line and we want to really understand what the shape is going to look like. Let's continue. Try 2. Well, that would mean we have to take the root of 2. We don't have a perfect square for that, but we could take it approximately on a calculator and that would give us 1.4. So at 2, it's about 1.4. Now that's just a approximation here. What would be the next number that would give us an exact value? Well, the next number that would give us an exact value would have to be taking the root of 4, because 4 is the next perfect square. So take the root of 4, you get 2. So we know that at 4, you should have 2. Okay, this keeps going. What's the next perfect square? Well, the next perfect square would be 9, so root of 9 is 3. So it's almost like the opposite of a square function. Remember, a square function gave us a parabola? When you plot this, you'll notice that this actually gives you a sideways portion of a parabola, which makes sense because the root is the opposite of squaring. Now, what happens at these points? Why have we not plotted anything here? Let's try some of those. -1 would mean we'd have to take the root of -1. Is that possible? We discussed that it's not. And neither will any of the other negatives be possible. So what is the domain? The domain is the set of all possible x values. So what is it here? Here, everything 0 and upwards will be possible and no negatives will be possible. So you can express your domain as x's are greater than or equal to 0. In the future, you can look at what is inside underneath your root and put it as an equation greater than or equal to 0, and you can then solve for x and find the domain. This is actually a nice thing to do at first because it helps you decide which x values to choose. It also tells you where you should probably start. Quite often, some people only graph part of the graph. You want to make sure you've graphed the entire graph. So if you're not sure, keep checking a lot of points. Let's take a look at another example here. We've got y equals the square root of x plus 3, and they also want us to find its domain. So the domain is actually just what numbers are possible for x and what numbers aren't. So what numbers are possible for x? Well, we know that under the root we cannot have a negative. So whatever x plus 3 is, it has to be greater than or equal to 0. Right? It has to be positive. It can't be negative. So that would imply, and you could think of this just in your head, or you could solve this. That would imply that x would have to be greater than or equal to -3. So that would be your domain statement. But let's see how that works. So let's try -3. What is it at -3? If you plug in a -3, you get root of 0, which is 0. So that seems to be the starting point because we have no other shifts around here. Continue on. So which way should we go? Now, if you haven't figured this out, you could just keep guessing numbers, but you definitely want to make sure you found that full iteration of that shape that we looked at before. So never quit until you've found it all. What if we chose a point that's less than -3? So -4, what happens with -4? Well, you get -4 plus 3, that's -1, and that's impossible, it does not exist. So there is nothing here. Everything exists past the -3. So let's try -2. -2 plus 3 is actually 1. So root of 1 is 1. So -2 gives us 1. Keep going. You might get a decimal because 2 over is usually not a perfect square, but let's try it. So -1 plus 3 is root 2. And root 2, as we found earlier, is 1.4-ish, approximately there. So the next perfect square would be 4 over from the starting point, which will be at 1. So let's try 1. That'll be 1 plus 3, which is root 4, which is a 2. So there we have it. And you can keep going. You know that 9 over is the next perfect square, and that's actually a 6. let's try 6. Plug in a 6, you get root of 6 plus 3, which is root 9, which is 3. So 6, 3. And you have the shape. So let's look at another example. Here we have more going on. We have numbers all around the root. So let's start playing with some x and y values. Now, the domain, remember, is going to only be affected by what's under the root. Whatever is under the root cannot be negative. In this case, you have negative x. So what kind of x values do you need to choose so that it'll cancel the negative? Well, you probably would want negative values in this case because negatives and negatives will make positives. So you probably want to choose x values that are less than or equal to 0. So anything less than or equal to 0 will cause you to get positives in the root. So let's try 0 because I think in this case we can still choose a 0. So that would be 2 times root of 0 minus 1. Root of 0 is 0. 2 times 0 is 0. That leaves us with negative 1. 0, negative 1. Okay, keep going. Now let's keep going this way with our intuition of the domain. So negative 1, let's see what negative 1 does. 2 times root of negative 1. So that's actually a positive one. So 2 times root 1, which is 1, minus 1 is 2 minus 1, which is 1. Negative 1, 1. Continue on. Now, when we take a 2, we know that we're going to be left with some sort of decimal, but let's try it out. 2 root negative 2, which is 2 minus 1. So you can use your calculator in this case. 2 times root 2 and then minus 1 would give you approximately 1.83. So let's try and plot that. For negative 2, you'd have 1.8. And let's continue to another number that's going to give us a nice perfect square. So that'd be negative 4. 2 times root negative 4 times a negative gives us 4. So 2 times 2 minus 1, that'll be 3. So negative 4 gives us 3. And let's try another number, say over here. Let's try this number. 4, 6, 7, 8, 9. Sure, let's do 9. Negative 9, 2 times root of negative 9 times a negative, which is positive 9. So that's 2 times 3, which is 6 minus 1 is 5. So negative 9 would be a 5. And so you can see that the curve has been changed a bit, but it's still got the same shape. It's actually moved down by 1 and doubled in its height. And it's also been flipped across to the left.